Well, this is John Black, super chemist. It's not that this light can't be higher, but these electrons can't make the light higher or lower because you can't throw the electrons to them to make them jump up high enough to go past their level of, without leaving the atom, right? It's not that the energy the energy can only be, but yeah, the only energy can be for these people, yeah, just like this. If I'm in this building and, all my rocks I throw down at you, right, they're all quantized, right, because the gravity is different in the same, here, different from here, but it's same, every time I'm here, you know what I mean? Each level, it's going to be the same amount of force that rock puts on the ground, you know what I mean? And it's going to be quantized, right? I mean, these people act like they've never seen the steps before. Have you never seen steps? You walk up the steps, yeah, it's quantized. Doesn't mean that, doesn't mean that the electron goes out of existence here, and then he pops into existence up here, okay? It's a mathematical construct. Just because these are so small, you can't see them jumping from thing to thing, and you don't have to just make up crap, right? You don't have to do that. Yeah, just tell the truth, right? Yeah, I want to make a clarification on the first. It's been a while since I made part 1 and part 2. I'm starting to erase my whiteboard to do, part 3, and I realized that I by human error, I copied down. I want to talk about these equations at the end, okay? But in part 1 and 2, I kept saying how they had these equations, figuring out the low frequencies, the higher wavelengths. But once it got up to about UV, when you were doing it so hot, heating up that whatever, glowing, that, the formula just broke down, right? I kept pointing saying, but this formula still works, you know what I mean, for, lower frequencies, you know what I mean, or higher wavelengths. This is not these are the equations, the Rayleigh-Jeans law equations, okay? That's what I should have been pointing to, okay? You can see they still have the Boltzmann constant in there. The T's, all these T's represent kelvins, temperature. Everything else is pretty obvious. That's joules per Kelvin, and this is Kelvin. See, those two things, that's energy. And we're going to get into that after this whiteboard. But they took into consideration this energy. And Planck took this, because this is Planck's equation, he has it too. K sub B times T. But he also added this H constant, this Planck's constant, right? So these two formulas, this one is for the wavelength and this one is for the frequency. That's why. And if you ever see this equation online or something, they use V for frequency. I use F because I'm not living in the 1800s. Okay, so I act normal. But anyway, see this, it does not work good once it gets to UV. You know what I mean? Once you heat something up and it's glowing, and it glows white, then it starts shooting out some more UV. Yeah, the equation doesn't work out. As the temperature gets higher, the frequency goes to infinity. You know what I mean? Meaning that you'd have be so much energy. But that doesn't happen, right? But it's a good approximation to the spectral radiance of the EM radiation as a function of the wavelength. What does that mean? That means it's approximate, estimation of the intensity of the light, using the wavelength as a function. Okay, meaning everything's based on the frequency of the wavelength. But it doesn't, because it has this. But it doesn't take into consideration. The H, does it? No, it does not. Okay. So they did these equations. The ultraviolet catastrophe was actually named after them. Some people call it the Rayleigh-Jeans catastrophe because their equation said this. You know what I mean? Once you heat it up, you should start getting frequencies so insanely, gamma rays and all this kind of stuff. But you can't. That isn't true. We knew it because we knew the actual curve. You know what I mean? we knew from data and collecting data, right, and doing experiments, we write down our data, you know what I mean, and then we plotted on a graph, so we knew that they were right, and this equation was wrong when you went up to higher, temperatures, where you're putting out UV, starting to put a lot of UV out. So what did Planck do? Basically, he took data from known experiments and plotted them on a graph, just like everybody else in his day did that were physicists, right? And he made a function equation. You know what I mean? He plotted the things and he made it, like up here with this. See where it says f of x equals x squared? That's a function, like in calculus. That's why these are functions. Both of these are functions. One's a function of wavelength and one's frequency. Okay. And like I said, he used h and k sub b, right, in his equations. See, these are both types of energy. He's taking taking account for both energies, whereas this guy, Raleigh and Jeans, is not. They're only taking care of one energy. Oh. So what is the Planck constant? It's the letter H, right? And this is what it's worth: 6.626 times 10 to the negative 34 joule seconds per cycle. Now all this stuff in red, or pink. I tried to make it pink, but I guess it's red. It says cycle or rad per cycle. Don't put them on. If you're going to college, don't bring that up to other people. But these are the actual. If you want to learn something so it all makes sense, use these, whatever they're called, units. This is joule second per cycle. And if you take it down to this basic units, it's Newton meter second per cycle. And then that's taken down to kilogram meter squared per cycle second. Okay. Now what is h bar, right? Reduced Planck's constant. Okay. That's taking the Planck constant and divide it by 2 pi. And that equals 1.054 blah 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 joule seconds per rad. See, these are different. See, if you talk to your teacher or whatever, your student, he'll say they're the same units, joule seconds. It's not true, okay? These are per rad, and these are for cycles. That's what they use these for angular momentum. That's why, because they use rads, okay? Now keep in mind, 2 pi, what is this? See, and this is what I'm saying. Use the units, then it all makes sense. This isn't 2 pi, it's 2 pi radians per cycle, okay? So if this is to convert it. This is just like if you have inches and you have kilometers. You have a conversion factor, right? 2 pi is just the numbers before the conversion factor. I could have this be inches and feet and have 2 pi here and say 2 pi represents whatever, you know what I mean? It's just a number. This is just a number, okay? And it's a conversion factor telling you rads are just like feet. They're just like inches. They're not something strange. They're just another kilometers, inches, miles. All those things, it's the same thing as a rad, all right? Let's look over here. If you have h divided by 2 pi, and you put the units in, right? I got the red and the blue units, right? This would flip over, right? Because it's on the bottom. So it would be cycle per rad. And the cycle would just goes down. Because you do the opposite. The bottom here, right, the cycle, goes down to the bottom. Here, the bottom cycle, it does the inverse. It goes into the top. So you cancel out your cycles, right? The red cycle and the blue cycle. And you're left with joule second per rad. Joule second per rad. The 2 pi is just to convert your inches into feet, or your inches into kilometers or whatever, right? And you might say, how does that make sense? Because 2 pi rad, right, which is you have up here, 2 pi rad per cycle, 2 pi rad per cycle, right? What's 2 pi rad? 2 pi rad is 2 pi radius. What's 2 pi radius? 2 pi r, right? Because diameter times diameter times pi equals 6.25 rads, or 25 radiuses, right? So what does this all mean, though? Look, here's a sine wave, right? Goes up and down, up and down. That is a whole cycle, right? That's what we call a cycle. That's what we're talking about over here when we say joule per second per rad, joule per second per cycle. This is a cycle, a whole up and down thing, one cycle. So how many rads is that? It's 2 pi rads. It's 6. Stop saying 2 pi. They need to stop saying 2 pi. It's 6.28 rads, right? Because if this is one cycle and you get 6.28 rads per cycle, right, like up here, and this is one cycle, then you have 6.28 rads, right? 6.2 radiuses per cycle. Okay, you have to think of this. If you took this over and you bend it over so you made this circle, right? It's actually an oval, right? But you have to pretend that it's a circle, right? Because a circle right here, here's the radius, right? 3.14 times 2 is this, 6.28, right? Which equals 2 pi. So every time you see 2 pi, don't think 2 pi, think 6.28, right? Because there's 1, 2, 3, if there's pi equals, there's 3.14 diameters in a circumference. So if there's 3.14 diameters, that means multiply that by 2, and you'll get how many radiuses you got, because a radius is half the size of a diameter, right? So you have 6.28 radiuses in this circle. This circle is a cycle. A cycle and a circle is the same thing. Okay? A sine wave, a cycle, a circle, they're all the same thing. They just mean you went around, you did some periodic thing and came back to the beginning. You know? And it makes the circular type shapes. You know? So 6.28, 2 pi radiuses, right, per cycle, because 2 pi r is a circle. That's how you get a circumference. You take the diameter times the pi, but in this case we're taking 2r, which is the same thing. And we're making a circle because one cycle equals one cycle equals one circle. See how they're the same thing? Okay, so what is a joule second, and what's a joule second per cycle, right? Each one of these waves down here, right? Each one of them, that's 1 second. I didn't do it perfect, but these should be the same space. You know what I mean? For all 3 of these waves, right? Because they equal 1 second, right? 1 second, 1 second, 1 second. Okay? Okay. Each one of these waves is a joule second. All of them. This is a joule second. This is a joule second. This is a joule second. Okay? But what does that mean? Okay? I mean, obviously it means this wave and this wave and this wave. But what does it mean? What it means is that this is 1 joule second, this is 1 joule second, this is 1 joule second, and you get a joule second, right? H is a joule per cycle every second, right? So this is 1H, this number up here, the 6.626 times 10 to the negative 34, right? That amount of energy, that many joules, right? This wave gets that many, it's worth that much joules, that much energy. Remember, joules is energy, right? So what is this Planck guy telling us? He's telling us that every time you have a cycle, every time you have the sine wave, every time you have a circle, every one of them, in every one of these cases, each one of these cases, that sine wave, this right here, this one single sine wave, right? There's 2 sine waves here, though. There's 3 here. Okay? Each one of them get an H worth, a Planck's worth of joules. This one, all these sine waves get the same exact amount because it's quantized into, just like eggs. You got so many eggs, an egg is worth something, okay? So much money. Well, each one of these waves, right, just a whole sine wave, gets this H amount of energy.